let's talk about how we can use calculus to find the length of a curve. So to set this up and to figure out the formula, let's think about this scenario. Say, for instance, for gym class, you have to log how far you walk during class, or maybe it's a homework assignment or something. I don't know. I don't teach gym. But your cell phone is dead. But you can't use your GPS app to track your walk. So you're walking through Archimedes Park on a curvy path, and this path doesn't have any distance markers on it, but the end of the path you found a map, and it has the equation of the path on it. What luck! So if you knew the equation of the path, or maybe you had a graph, right, what would you do to find how far you would walk? Well, one thing that we do a lot in calculus, right, is we partition things up into really tiny sections, right? When we found area between curves with Riemann sums, right, we thought about partitioning the area up into tiny little rectangles or trapezoids to figure out what the area was, and we just added them all up. So to find arc length, we can do the same thing and just partition the length of a curve up into tiny, tiny little pieces, find the length of each piece, and then we can go from there by adding them all up. So say, for instance, we start at point A. iPad is spazzing out today. Okay. All right, so say we start here at point A, and the first point I'm going to mark to is here. So say I had a ruler, maybe, and I had a map that was drawn to scale, so I could draw these little straight lines around it. So I'm going to call this first point x1. Actually, we'll do x0, y0 for our starting point, and this can be x1, y1. So if I wanted to find the distance, I'll call this distance 1. Right, we know from geometry class the distance formula is just the square root of the difference between the x's squared plus the difference between the y's squared. Right, basic Pythagorean theorem. Okay, so say we took another section now. So say now I go here. So I'll call this x2, y2. Right, and this would be distance 2. Right, so then I would have x2 minus x1 squared plus y2 minus 1 squared. Right, and we would keep going along like that along the whole line. Right, so say we did that for the whole thing. Right, so then to find the total length of the line, right, so my total distance, total is not spelled with a D. What am I doing? Would equal the sum, right, of the DI's, meaning that all of those little individual distances that we get. And we know that a sum in calculus class is represented by a sigma. And we'll let it go from I equaling 1 to n, however many times we go. Right? So if we think about this, if you let the distances get smaller and smaller, if you let the distances between our different points get smaller and smaller, we can really think about this as if we generalize. I don't know why I cannot speak today. If we generalize our distance formula, we get that it's really the distance in x squared plus the difference in y squared. Okay, and as we let the differences become really small, so as we measure in smaller and smaller segments, so I'm not taking these big jumps anymore. So say now I'm going from here to here and then from here, right? We're letting the distances between our points get much, much smaller, right? We can say that these are becoming infinitesimally small, right? So we can kind of say this. I'm not writing this in super formal calculus, but that's fine, right? So as n goes to infinity, so as the number of these little segments gets bigger and bigger, right, we can say that this really the delta x has kind of become a dx and the delta y has kind of become a dy. So we can say that our distance would be equal to the square root of dx squared plus dy squared. And if we do and we're doing the sum of this, so now we'll make this a little formal, right? The limit as n goes to infinity of, right, the sum from 1 to n, and we're going to plug this in now. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . right? And we know that the limit as n goes to infinity of a summation like that actually turns in to a definite integral from a to b. And now let's just do a little bit of manipulation here. So I'm going to run out of space. This was poor planning on my part. It's fine. That's what the add page button is for. Right, so all I'm going to do is, because this doesn't look totally like an integral yet, so I'm going to just factor dx squared away from the inside. So that's going to give me 1 plus dy squared over dx squared. And then if I take that out, I'm just going to jump down here to give me more room. Shoop. Right, if I take the square root of this part now, we get a dx, and I'm going to bring that to the end, of 1 plus dx dy, over dx, right? And that's all being squared. And then we know that dy over dx is the same thing as the derivative. So I can say that the length of the curve is actually the definite integral from the starting point to the stopping point of the square root of 1 plus the derivative squared. And that little distance formula is actually kind of how we come up with that. And you just take a limit as you would add all of these infinite little pieces up, and that's how we get the definite integral. So not a super formal proof or anything of how we get the arc length formula, but at least a little bit of like, where does it come from? So the arc length of a curve, this is often referred to as S in math. I do not know why, so do not ask. That's an easy Google question, though, I imagine. So either I could research it and tell you in class, or you could Google it yourself, because you have all those resources available to you as well. But our arc length is equal to the integral from a to b, the square root of 1 plus the derivative squared dx, right? Or you can take this as a dy integral as well. So f prime of y all squared dy. So the cool thing about arc length is if you take it in terms of x or if you take it in terms of y, it's a length, so you're going to get the same distance no matter what. So a lot of times it's just whatever is going to be easier to integrate if you're going to be forced to do it by hand. Or maybe like the derivative is easier to take in one direction if it's defined with y's instead of x's or something like that, depending on how they give you an equation like that. So let's go ahead and use this formula. We're going to do a few problems both with the calculator and without the calculator. So I am just doing this on my iPad, so I don't have the emulator up. So I will just kind of like walk you through how to do this on the calculator too. So we're going to find the exact length, which means that we are not going to use our calculators, of the curve y equals the natural log of the secant of x from 0 to pi over 4. So the first thing we want to do is find our derivative. So the derivative of natural log is 1 over whatever inside times the derivative of the stuff on the inside. So the derivative of secant is secant x tangent of x. Right, so that's really over 1. My secants are going to cancel out, so we get tangent of x. So my arc length, my s, is going to be the integral from 0 to pi over 4 of the square root of 1 plus tangent of x all squared dx. Okay. I'm going to start writing a little smaller. So what we get here is, if I could use my pen, right, we know that's obviously the integral from 0 to pi over 4 of the square root of 1 plus tangent squared. And so now we're doing this without a calculator, which means that this must be able to be integrated. So 1 plus tangent squared should hopefully bring up the idea that we have the Pythagorean identities, right? It looks a little bit like Pythagorean theorem. And so if we think about our Pythagorean identities, we know that 1 plus tangent squared of x equals secant squared of x, right? And that just comes from sine squared plus cosine squared equals 1, right? You would divide everything by cosine squared to get that equation out there. So I'm going to go ahead and exchange that 1 plus tangent squared for secant squared of x, because that's their equivalencies. Okay, well then I know that the square root of secant squared is just secant of x dx. And then I know how to integrate secant. That's just the natural log of the absolute value of secant x plus tangent of x. Right, and we're evaluating that from 0 to pi over 4. Okay, so we got natural log. So if I plug in pi over 4, the secant of pi over 4 is the square root of 2, right, plus 1 for tangent of pi over 4, and then we have minus, let's see, natural log, we got secant of 0, that's really cosine of 0, 1 over that is 1, okay, and then we got tangent at 0 is 0. Okay, so we get the natural log of the square root of 2 plus 1 minus the natural log of 1, and the natural log of 1 is really a 0. So our final answer, the exact length of the curve here, is the natural log of the square root of 2 plus 1. Okay, let's try another one. So again, we're going to do this without a calculator. So we're going to find the exact length of y equaling 4 square root of 2 over 3 times x to the 3 halves power minus 1. So again, anytime you're asked to find arc length, you want to first start by finding your derivative. So I've got 4 square root of 2 over 3, and then if I do power rule, I'm going to have 3 over 2, x to the 1/2. Let's see, so my 3's are going to cancel out, and I can reduce this to 2. So this is really 2 root 2 times x to the 1/2, which we can also think of 2 times the square root of 2x. So if I do my arc length now, and I'm doing this from 0 to 1, got the square root of 1 plus my derivative squared, right, dx. Okay, so that's going to be the integral from 0 to 1 of 1 plus 4 times 2x, so that's going to give me 8x dx. So I'm going to go off to the side and just do a quick little u substitution. I'm going to let u be 1 plus 8x, which means my du, if I take the derivative, would be 8 dx. So 1/8 du is going to equal my dx. Right, so substitute that in. I'm also going to substitute in for the limits of integration, so that way I don't even have to convert it back to x's. So if x is equal to 0, that means that u would equal 1. And if x is equal to 1, u is going to equal 9. Okay, so if we go ahead and substitute in here, right, my limits are now going to be 1 to 9. And I'm going to have the square root of u times 1/8 du. Okay, so that's going to be 1/8. If I do my power rule of integration, right, I would add 1 to that power. So that would be u to the 3 halves divided by the new power, so reciprocal of that. And then we're evaluating from 1 to 9. So that's going to give me 4, 1. Okay, so this is going to give me 1/12 of u to the 3 halves from 1 to 9. I'm going to leave the 1/12 on the outside while I evaluate this. So 9 to the 3 halves power minus 1 to the 3 halves power. Okay, so 9 to the 3 halves, square root of 9 is 3, 3 cubed is 27, 1 to the 3 halves is 1. So we're going to get 26 over 12, which is 13/6. So the exact length of that curve is 13 over 6 between 0 and 1. Okay, and then let's do one more example problem. We're going to make this a little bit more realistic, so we're going to do kind of an application question, and we are going to use the calculator for this. So an electric cable is hung between 2 towers that are 200 feet apart. We have a little graph of that there. And the cable takes the shape of this curve. That's called a hyperbolic cosine, or the cosh. So anytime you hang a wire or cord between 2 points like that, it forms this hyperbolic cosine function, which can also be expressed with e's. So it's 750 times the quantity e to the x over 150 plus e to the negative x over 150. And we're going to find the length of the cable. Okay, so the first thing I need to do is figure out my derivative. So that's going to be 750, right? And then if I take the derivative of e to the x over 150, that's the same thing, times the derivative of the exponent. And if I take the derivative of the second part, it's the same function right, times that negative 150 from the exponent. Okay, so 750 I believe is actually divisible by 150. It is, so I can write this as, right, 750 times 150. If I bring that out, e to the x over 150 minus e to the negative x over 150. So that's going to then give me 5 times e to the x over 150 minus e to the negative x over 150. So there's my derivative. And I want to find the length of the curve. So based on the way that they have set up the graph, right, that's going to be from negative 100 to 100. Right, and then I have 1 plus the derivative I just found. And then I'm going to square that and put that all inside of a square root. Shoop. The 1 is kind of hidden now, but that's okay. Right, and then we're just going to carefully type that in on my calculators. So I'm going to go to Math 9, and then I'm going from negative 100 to 100, type in my square root symbol, 1 plus, opening parentheses, 5 times e to the x divided by 150 minus e to the negative x divided by 150, close my parentheses and square them under the square root, put an x in for my dx, hit enter, and then luckily it didn't take too long. So that means that there's approximately 385.510, my unit here would be feet, of wire between those two towers.